Hello, everyone. Good morning in Chile. Good afternoon in Europe. Thanks for the opportunity. And I will give you a very brief summary of the MOONS project on behalf of the consortium. And just the takeaway slide is that MOONS will use the largest field of view at the VLT, which is 500 square arc minutes. It's got 1,000 fibers, which can be either deployed independently or in pairs if needed. Has got the capability of put the fibers quite close to each other, down to 10 arc second. And it's got very simple modes of operation. It's got medium resolution, where you get from 0.64 to 1.8 microns simultaneously at a resolution of 4 to 6,000. Or you go to high resolution, in which you switch the 9,000 resolution around the calcium triplet and 20,000 in the H band. And the system has been optimized to have very high throughput, larger than 30%. Just to give you a bit of update on the status of the instrument itself, since we are ISO. So you can find some more news on the website, which is there. And you can see here the rotating front end, which is the one that hosts the fiber positioner, has been completed with all the mechanisms movings, all the supporting structure and the cable wrap done and completed. The fiber positioning units, which are the ones that carry the fibers across the focal plane to be positioned with an accuracy of 15 microns, which is 50 milliarc second on the focal plane, are all in final production, and 500 of them are already being installed on the focal plane and tested. And as I said, we covered the entire field of view of the VLT with this tiled focal plane. And because we have made such a close pair of the fiber positioner, they can collide. Therefore, we had to develop a path analysis and observation preparation tool that allows this very accurate and very efficient allocation with this positioner dancing around each other to be able to go to their final position on sky with a very fast configuration of the order of one minute. Also, the cryostat has been completed. As you can see here, is huge, is almost 4 meters in high, and holds very well the vacuum. And we also have all the fixed optics, the gratings, the dispersers, the dichroics has been completed, and they are in the final mounting stage. They've been also tested inside the final cryostat. And the cameras, which are some of the fastest cameras in astronomy, are now under final alignment in the cryogenic environment and ready to be installed for the final assembly in the telescope. And what we aim at is to have, as I said, very high throughput in the system, above 30%, which translated for astronomy means in an hour integration, we hope to go down to 2 or 3 10 to minus 17 ergs per second per centimeter square, 5 sigma. But also in the continuum, after doing sky subtraction, you can rebeam down to a resolution of 1,000, go down to AB 22.7 or even 23. And in the high resolution mode in H, in Vega, a 15.5 magnitude with a signal to noise of 50. So the whole system is really optimized for this. We also made a simulator to help us to get the data reduction software to make sure that we can really subtract the sky and reach this sensitivity. In terms of science, which is more for this audience, so the idea with MOONS has always been from the very beginning to be able to observe galaxy evolution across the entire history of the universe. From our Milky Way, as we were saying before, we do galactic archaeology across the entire history up to the very, very first galaxies at the epoch of reionization. And let me spend just a few words on the galactic service, which will account for 100 nights of the GTO. And the idea here is to really exploit what MOONS is good at in the using the near infrared part of the instrument, which is studying the central part of the galaxy, the bulge, the thick disk, the thin disk. And you can see here various pointing covering the entire central part of the bulge of the disk, and also going outside in some globular cluster, and also covering the Milky Way satellites, both in terms of Magellanic Clouds and the Sagittarius Dwarf, again, pointing in the critical part of the galaxy and getting both chemical abundances and radial velocities for both the central component of the Milky Way, as well as for the Milky Way satellite. But then move on to the more topic for this conference, which is the extragalactic universe, for which Moons will dedicate 200 nights of GTO nights. And we defined one single self-consistent survey called Moonrise, in which we really try to exploit at the best the characteristics of the instruments. One is the wavelength coverage. Because we cover up to the full H band, there is a sweet spot in redshift that goes from redshift 0.9 up to redshift 2.5, where the instrument is capable of seeing all the key spectral features, both for emission line and continuum, to give you all the physical and chemical diagnostics for both passive and star-forming galaxies. And the other key aspect that Moons does is that it packs 1,000 fibers over the field of view, and therefore can exploit a very high density target multiplexing, able to really go and explore the environment. So getting clusters, groups, pairs, really over the overlapping of the FPUs has been designed for this, really targeting the high density environment, and combining this environment and chemistry and physics is exactly at the core of the Moonrise survey, which will employ 2 million fiber hours at the VLT. And the idea is to combine volume, number, diagnostics, and high sampling to obtain spectra for almost 500,000 galaxies. And here I give you some of the high-level tier optimized observation strategy, in which we focus, first of all, on the redshift range from 0.9 to 2.6, with a combined selection where we observe all the galaxies down to 23.5 or 24th minus in H, as well as all the galaxy with a mass limit of 9.5, 10 to the 9.5. And then we have a component, a high redshift, but also we'll observe targets at this redshift outside these two. And again, the idea here is to maybe compromise a bit on the area, but to do very long exposures to have high signal to noise. For a subset of sources, we will push up to 40 hours. And we want to have a very high sampling rate, 70, 80% of all the galaxies in our select section box. And we're going to pass over the same part of the sky multiple times to really make sure that we have this high sampling rate and therefore sampling the environment of the objects. Doing this, we should be able to cover of the order of 10 square degrees, covering cosmos because of the multi-wavelength data available there, as well as 2 of the video fields, one in the extended channel deep field south and another one in the XMM LSS. And now I would like to give you a few examples of the science cases that the team has been putting together. And the slides that I'm going to present are really fully credited to the working group that's been working on it. And at the bottom here, you can see the names of the coordinators for each of the working group. And we start with the physics of the interstellar medium, led by Filippo Mannucci and Lucia Pozzetti. The idea is to really get all these key diagnostics to get, for example, the gas metallicity, both from the strong line methods, but also using the auroral lines and getting, because we see both H alpha and H beta across most of that range, we also can get absorptions and star formation rate, but also looking at the relative chemical abundances, for example, N over O, S over O, or the alpha over iron, and see how they evolve across the redshift range, but also looking at the ionization properties, looking at, for example, how the ionization parameter changes, or there is changes in the densities of the ionizing continuum. For example, this is a plot taken from the Mossfire survey, and you can see that there are 300 objects that can be done in less than an hour with the Moons, a couple of hours with the Moons survey. And finally, also we can look at dynamics. This is a work that Alice Concas is working on, presented before. And the idea is to look at the profile of the lines to get the dynamics and possibly the outflows for the galaxies. Another key component is not only to look at the emission lines, but also at the continuum, both for star-forming and passive galaxies, well past the M star of the mass function at this redshift. Also, not only to look at the evolution of passive fraction, the fraction of passive galaxies as a function of redshift done in spectroscopy, but looking at the spectra for the bright sample, looking at individual objects, but also in stacked spectra, looking at ages and star formation history, as well as looking at the stellar metallicity, not just the gas metallicity, but also comparing it and obtaining stellar metallicity through long exposures to compare how the mass metallicity relation changes both for gas and stars. Almost as a byproduct of the survey, you're also going to look at the content of the AGN, because we do a very simple selection in magnitude and mass. The AGN will come up for free almost, and we can look at the evolution or the coevolution of the mass in stars and the mass of the black hole. But again, one thing which is peculiar to moons is to look, for example, at the fraction of obscured objects. Because we can go deeper, we can go in the near infrared, we can look at those AGNs which are type 2 AGN or Compton-Tick AGN, and therefore do a very good census of the AGN activities at high redshift. And all this has to be really constrained and combined with the environmental measurements. So all the physical content will go together in the surveys with measurements of the environment, which run from the really understanding how galaxy evolution depends on the halo mass, the fraction of central versus satellites, how the quenching mechanisms, and all looking at galaxy groups, pairs, local density fields, mergers, filaments, clusters, and protoclusters. So all these things of physics and environment for the first time at this redshift, and with such a high completeness, over 80%, can really go hands in hand, and we can reconstruct the nature versus nurture effect at this redshift, as has been done for the local universe. Finally,
5 minutes.
I'm almost finished. One final thing, at the very high redshift range, at the epoch of reionization, again, moons is extremely efficient for exploring this epoch of reionization, because it extends from the J up to the H band, as you can see in this plot. And first of all, we can look at the evolution of the neutral fraction through the Lyman alpha, just observing Lyman alpha. And because we cover a large area, we can also look at the topology of the reionization and trying to get in the three-dimensional clustering of this bubble of reionization that will occur at this redshift above 7. But because we also can observe other lines like carbon-3, carbon-4, we can also look at the ionization state of these very primeval galaxies. At the moment, the number of galaxies for which we have these measurements is extremely small, and this will come within the large surveys. We can allocate some of these fibers as we do the lower redshift surveys. We can allocate some of these fibers to these high redshift objects and really try to get as deep as we can to get not just Lyman alpha, but also other lines. And at the end, trying to get the holy grail of the epoch organization, which is searching for the signature of POP3 stars, for example, trying to measure helium-2 lines in some of these galaxies. So in summary, MOONS is the long-awaited infrared multi-object spectrograph for the VLT. It features 1,000 fibers covering simultaneously from 0.64 to 1.8 microns at a resolution of 4 to 6,000 when you work in the low resolution mode, or up to 20,000 in the H band when you work in the high resolution mode. And really is the best instrument to work on the obscured regions of the bulge and the disk, but also providing a formidable SDSS-like survey to study galaxy evolution across the peak of mass assembly up to the epoch of reionization. And somehow, as Sophia was telling, closing the loop and going from galactic archaeology in our Milky Way across all the cosmic history up to the formation of the very, very first galaxies at the epoch of reionization. And we are aiming to be on Sky by starting surveys by late 2023. Thank you.